So we met the definition of the Laplace transform, and we're going to see our first few examples now. So for a function f of t, the Laplace transform of f of t is defined as this integral, the integral from 0 to infinity e to the minus st f of t dt. Now the things to notice here is that a new variable has been introduced. So this integral, the value it has, depends on what value that quantity s has. The thing is no longer a function of t. T does not have a particular value. T is integrated out over all of its domain. Most of the time in these applications, t is a time-like variable. So we think of t starting at 0 and moving on. So we're integrating over all possible values of t, the exponential e to the minus st f of t dt. So this is a new function of the variable s, of the new variable s. Formally, although it won't have that much consequence for us, but formally this new variable can be any complex value. And this is why we attach the word transform to it. So a transform in mathematics, it's just a particular word used for it. A transform in analysis or calculus normally indicates this process where you take a function of a certain variable and you get out a new function of a new variable. Such as like this. Okay, so this transform is taking account of every value of f, and we're packaging them up, multiplying this exponential expression e to the minus st. So we're kind of packaging up all the values of the function f, feeding them all and using them all to generate this new function, which is a function of the variable s. Okay? And sometimes this is notated, sometimes written. That the Laplace transform, we use various notation for it. Sometimes we use capital F of S to denote it, so the capital version of the lowercase name, the original name of the function, or sometimes we'll call it F hat of S or F bar of S. Some kind of, there are various authors and books will use various notations. So some kind of notation to indicate it's a new function of a new variable, somehow related to the original function. And the integral can converge as long as the function f is eventually dominated, meaning less than, dominated by an exponential function e to the alpha t, where the thinking here is alpha is really the real part of s. And this really means most standard functions, okay? Because exponentials increase very, very fast. So providing the function f we're dealing with is eventually dominated, eventually less than some kind of exponential function, then this integral will converge for some values of s. So some examples. So some examples for some simple functions f. These are done on page 41, but I'll just talk about them. So a constant function. E.g., well, what kind of constant function? Well, I mean, the simplest constant function would be the zero constant function. I mean, you could look at that, but then you're just integrating, well, you've got a zero factor in there, so you're integrating zero. It's going to be zero. Nothing much happens, so to speak. So maybe, and really, the first non-trivial case would be a constant function which takes a non-zero constant value. So let's look at the constant function 1. So our function f is just the constant value 1, constant signal 1. Okay. So what's the Laplace transform of this? Well, we just apply the definition. It's the integral from 0 to infinity, e to the minus st multiplied by f of t dt. Okay. But f of t here is just the constant function 1. So there's nothing really more to write down. Now, I could write down multiply by 1, but I won't. Okay. So it's this integral. So, well, okay, so this is maybe the simplest way this integral could be. We don't have another factor here to deal with. It's just the integral of the exponential. And we all know that exponentials integrate to themselves, although you may need to adjust if there's some factor here multiplying the variable, which there is here, minus s. So you need to divide by minus s. So that's the integral, and this gets evaluated at 0 and infinity. So in other words, this is the limit as t goes to infinity of e to the minus st minus, so that's the evaluation of it at infinity, minus the evaluation of it at t equals 0. Well, at t equals 0, you've got e to the 0, which is just 1. So it's minus 1 over minus s. Well, remember, we talked about this last week. If your complex value is a plus ib, where a and b are the real and imaginary parts, so a and b are both real numbers, then that exponential splits up as e to the minus a t by e to the minus ibt. And this is going to be plus 1 over s. Two minus signs. Because if s is a plus ib, then using rules of exponents, this exponent of a sum becomes the product of the exponents. Okay, we can understand the behavior of this quantity as t goes to infinity. The exponential e to the minus ibt. Well, this is just e to the I times something. E to the I times something, we know, is a point on the unit circle in the complex plane. So this number, whatever it is a complex number that always has magnitude 1. So it's just spinning around the origin as t goes to infinity. This quantity here is a real exponential factor, and we understand how this behaves. If the quantity a is positive, then we've got e to the minus something positive times t. Well, as t goes to infinity, that's going to go to 0. If a is negative, then that's going to be e to something positive times t. As t goes to infinity, that's going to explode in value. E to something positive, that the positive exponent is getting larger and larger. So as long as this quantity if a is positive, then this exponential here is negative and getting larger in negative magnitude as t goes to infinity. So this factor is going to converge to 0. This factor is always stuck circling the origin at distance 1. So when you multiply them together, they're going to circle towards the origin. Okay? So basically, the limit, that whole limit is going to be 0. It's not going to be there as long as a is positive. So we just get the quantity 1 over s for a, which is equal to the real part of s, as long as that's a positive number. Okay? So the Laplace transform of the constant function 1 exists as long as the real part of your argument s, as long as the real part is a positive quantity. Okay? If a is negative, then e to the minus at diverges as t goes to infinity. So the integral doesn't exist. But here we see our first result of a Laplace transform, that the Laplace transform of the constant function 1 is the quantity 1 over s. We could look at, say, a second example before we continue to look at properties. So our second example would be the identity function. F of t equals t, okay, or it's the 45-degree line, the identity function. Maybe the next simplest function after a constant function. Okay, it's a function which just has a constant rate of increase. What's its Laplace transform? Well, we can apply the definition. That's the definition of the Laplace transform. Okay, it's slightly more complicated. This time we have to integrate the exponential multiplied by t. But that kind of thing, we can see that this needs integration by parts. So you can either look up what the integral of t times an exponential is, or you could carry out the integration by parts. Carry out the integration by parts, you would recast the other exponential factor as a derivative. That's the derivative of minus e to the minus st over minus s. So now we see the integral as an integral of one function times the derivative of another. So we can apply integration by parts. So it's going to be t times this e to the minus st over minus s. This evaluated at 0 and infinity, minus the integral from 0 to infinity of this factor within the brackets multiplied by the derivative of that one. Well, the derivative of t is 1, so we just have this factor here in the brackets. Okay, so that's carrying out the integration by parts. As before, when you do this evaluation here, when you evaluate it at the limit infinity, you're taking the limit of this expression as t goes to infinity. So that is the limit of t times an exponential function. Now, an exponential function is a constant rate of increase. The exponential, if the real part of s is positive, this exponential is decreasing to 0, converging to 0 very, very fast. If the real part of s is negative, then that exponential is going to be exploding in value very, very fast. So the convergence of this factor still comes down to the behavior of the exponential. So as long as the real part of s is positive, we will have convergence here. We'll have convergence to 0 as t goes to infinity. And when you evaluate a t equals 0, well, you've got a factor of t here. When you evaluate that at 0, so that's going to be 0 minus 0 for the evaluation of that square bracket. This integral here, the 1 over s I can take outside, because the integral is an integral with respect to the t variable. Remember, s is a new variable. It's independent of t. So in this t integral, this s just acts like a constant. So it can move outside. But then this integral is the one we just did a moment ago. It's the one we just did up here. And it had the quantity 1, it had the value 1 over s. So that becomes 1 over s squared. As long as the real part of s is positive again, the Laplace transform of the function f of t equals t is 1 over s squared. So that's our first couple of Laplace transforms we're seeing. Over the page, in the notes it's pages 42 and 43. They're numbered slightly differently because I've taken them from the formula handbook. So this shows you the table of Laplace transforms that we work with a lot. This is something you'll have in the standard formula handbook in the exams. So down the left-hand side, we have a lot of standard functions, beginning with the constant function 1 and the function t, the ones we just dealt with. And over in the right-hand column, we have their Laplace transforms. Okay. So we can set ourselves a number of exercises to derive each of these. Okay. You just keep the talk down. We should set for ourselves a number of exercises to be able to justify all these Laplace transforms. We've justified the first couple. But we might come back to elements of that as we go on. Now, there are other entries in the Laplace transform table as well, which are more to do with properties that the Laplace transform enjoys. We'll refer, as we pass through each of these and discuss each of these, we'll point them out on the table as well. So the initial work we should be doing with the Laplace transform is getting familiar with calculating it for particular examples, but also starting to think about proving by not just certain instances of certain functions, but starting to think about what properties the Laplace transform might have. And in the remaining 3 minutes, we can prove the first property, because it just comes straight away from its definition. The Laplace transform is linear. It's a linear transform. Thank you, please. So it's a linear transform. Now, what do you understand by that term linear? You have to take that and apply it to this context. So linear refers to how it behaves on linear combinations. Now, the Laplace transform is something that acts on functions. So we have to imagine functions f and g and imagine a linear combination of them. So we've got functions f and g, and we've got real numbers alpha and beta. So saying the Laplace transform is linear is saying that when you apply it to a linear combination of functions, you get the same linear combination of the individual transforms. Okay? That's what we would understand by the property linear applied to the Laplace transform. Well, the proof is just a very simple, just a one-line justification for this, okay? Okay, please, can we stop the chatter? Thank you. The Laplace transform is built from integration. And integration is known to be linear. Integration is known to be linear. And because the Laplace transform is just a certain kind of integral, it too will inherit that linear property. So when we take the Laplace transform of a linear combination of functions, we're integrating the exponential times those functions. After you multiply out, I mean, you're integrating the exponential multiplied by alpha f plus beta g, but after you multiply it out, you've got the exponential times f plus the exponential times g. You've got those scalars alpha and beta, but integration is linear. So this integral is alpha times the integral of the exponential times f plus beta times the integral of the exponential times g. Okay, you apply the definition, you multiply it out inside the integral, and then you apply the known linearity properties of integration. You get this expression here, but of course this is just exactly alpha times this thing, but that, what is that? That's exactly the Laplace transform of f. And this is exactly the Laplace transform of g. So you can summarize this proof as saying, well, why is the Laplace transform linear? It's linear because integration is. The Laplace transform is a certain kind of integral. Okay? So it inherits that property from integration. So next time we'll continue our approach of looking at certain examples of the Laplace transform and starting to accumulate some known properties. Okay, we're finished there for this morning, this afternoon.